This section comes in 4 parts, acid-base titrations, and when I do it in the lecture Zoom, I will have more time and I will maybe even do it in a different way. But to get this up on YouTube, this is how I decided to do it. There are 4 parts. So what is a titration? Well, that's where one reactant is slowly added to another. You do monitor things, okay? You do monitor them. Where do we use titrations? Well, sometimes we want to find out concentrations. I put here reactants. Sometimes we want to find out equilibrium constants, most likely Ka of weak acids. What do we usually use? Well, we use something that's going to change color, an acid-base indicator, and there are many different types of titrations. Does a strong, weak acid base make a difference? And the answer is yes. So what you're going to be doing here is calculating pHs. You're going to need your stoichiometry skills. You're going to need your ice skills. You're going to need all your salt calculation methods. It is laborious, okay? So normally we use a pH meter, which is really a digital readout. We do use an indicator to monitor when we go through the equivalence point, but let's take it one step at a time. We plot the pH on the y-axis versus the volume of the added titrant, and that is what defines a titration curve. You can read the pH directly off the pH meter. It has a readout, or you can calculate the pH from known additions to titrant. So as you go further and further, what you can do is you can plot this and calculate it, and that's essentially what you'll do on an exam. The color change of the indicator, that plays a key role. That tells you when you have gone through the equivalence point where there is an equal number of moles of acid and base. Okay, shape of the curve. What does it allow you to determine? Well, that we had this back in chapter 4, the equivalence point. That's where we have chemically equivalent amounts of moles of acid and moles of base. The range is anywhere from 1.5 to 2 pH units, and it can go really, really fast. An important point is the half equivalence point. You're going to say, why? Well, here your pH measurement is actually equal to your pKa or your Ka. It's the volume, half the volume that is required for neutralization, all right? Then there's another point called the end point, and that's the point during the titration where the color actually changes. You may have a rough idea about that now, and that change, it's determined by the Ka of the indicator. So there's a lot of things that are going on here. Ideally, the color change and the endpoint, they should coincide. Phenolphthalein, also known as X-Lax, it is colorless before 8 and red above 10. So what is this indicator? Well, it's actually a weak acid. In minus, I say it has color 2. It has a different color than HIN, which is color 1. Stoichiometric calculation, equilibrium calculation, those are the 2 calculations you absolutely must know how to do. And you do know the methodology. What you have to do now is put everything together. I listed 6 different types of titrations. We only do numbers 1 and 2 in this class, but number 1 is related to number 3, and number 2 is related to number 4. Polyprotic acids, oh, those are challenging, but they can be done. But any weak acid, weak base, it is beyond the scope of this text. Okay, so what else do we want to say? Well, when we have a strong acid, strong base titration, our pH at 7 is going to always be 7. That's the equivalence point. And what you're going to do is when you run these calculations, you will see that very small amounts of our base, if we're titrating base with acid, it's going to have a very rapid pH change. So you want to pick an indicator based on that equivalence point, and we say any indicator that changes color between pH 4 and pH 10 will work for a strong acid, strong base titration. So I list 2 of them here. One of them is methyl red that changes in the, I'll say, acidic range. The other one is phenolphthalein that changes in the basic range. If you're doing this in the lab, you need many points. You can't just do 3 and say, done. You have to really do a lot of points. Now, what you might be surprised is these calculations, they depend only on the milliliters and the molarity and not on the identity. Because what you're doing is you are titrating H pluses and OH minuses. So the first calculation we're going to do, that's called part 2. It will be using the strong acid nitric acid. We will be titrating it with the strong base, sodium hydroxide. And what you have to know is that being a strong acid, it dissociates 100% to H+. Being a strong base, it dissociates 100% to OH-. Then the H+ and the OH- do the neutralization reaction, the same they did in Chapter 4, but we did not do extensive calculations. We're going to have 4 different regions that I will draw on a picture. Okay, we kind of go there. Here we have our pH on one side. We have our mLs of OH- added. We will have a curve that looks like this. We will call this one initial. We will call this halfway. We will call this the equivalence point. We will call this the acid region, and I will even put the word excess in front of it. And we will call this region the base region, and I will put the word excess in front of this. You will see in part 2 what the respective pH calculations are.